This is our second substantive lecture. I hope you have listened to my description of the project and what it is and why it is needed. Okay, so actually, it's the first substantive lecture, right? All of the administrative we have already covered, and you are comfortable, I hope, with what to expect. So let's now go through the actual stuff. So today we'll just cover simple stuff, foundations, right? What is learning? Why? What are we really doing here? And I think I can do it the following way. Yeah. So outline for the lecture. We'll just figure out what is the problem that we're solving. Like, let's just try to formalize the problem of learning. And the second one is we'll talk about inductive bias, something that will help us solve that problem. And then we'll try to bound the probability of error of our learner. And let's go on. Problem statement. So imagine that you have just arrived to some small Pacific island. You soon find out that papayas are a significant ingredient in the local diet. However, you have never before tasted papayas. You have to learn now how to predict whether a papaya you see in the market is tasty or not. Well, first you need to decide which features of a papaya your prediction should be based on. And on the basis of your prediction, or of your previous experience rather, on your previous experience with other fruits, you decide to use two features. Let's just simplify our exposition with limiting it to two features. The papaya's color, ranging from dark green, like on the picture, most of the fruit, through orange and red to dark brown. And the papaya's softness, ranging from rock hard to mushy. Your input for figuring out your prediction is a sample of papayas that you have examined for color and softness and then tasted and found out whether they were tasty or not. So imagine you've tried 10 or 15 papayas of various composition of those two features. So let's analyze the task, this papaya selection task, or what should your algorithm be of learning a papaya classifier. And we demonstrate by analyzing these tasks, you will see some formalization of the learning theory. So, setup. Let's start with chi, the domain set. So our domain set in this papaya example is all papayas, or all data samples, all possible, not just the ones that we already tried or sampled. Then label set y is, or label set of all papayas, 0 or 1. Say 1 is tasty. Then another thing is sequence S here. The sequence S is often called a training set. It's a sequence of pairs of data sample and a label. And again, this is a set of two numbers, 0 and 1. Say 1 means tasty, just so you have this full picture. So as you see, the set sequence of samples with the corresponding labels, in our case papayas, well, x in our case is a two-element vector, right? x1, x2, where x1 is color and x2 is softness or hardness. So we have that, and as you see, the set is a Kronecker product of the set of all papayas, and like the set possible set S or complete set S will be Kronecker product of the domain and the label set. Okay. Now, let's say our learner or our learning algorithm considers S, but what it needs to return, what we're after, is H, which is our prediction rule, aka classifier, aka hypothesis, aka predictor. And it's a function of that maps from the domain set to the label set, which means that our predictor or classifier takes x sub I as an input and should return a y as an output. So our learner is a process that, as a result, returns a function. As you see, this classifier is the output of our learner, of our learning algorithm. And then what we also need to define, we need to define a simple data generation model. And that data generation model includes D, includes capital D, which is a distribution of papayas. And it includes, or we assume in today's lecture, it includes a true labeling function. So this is tricky because, well, you understand F is our true H, right? If we can recover from data or from training samples S, if we can recover F, we're as happy as we can be, because that is our goal. But the actual presence of F is tricky, and this is what we assume. We assume that every possible papaya can be either declared ripe or not ripe, or rather tasty or not tasty. And in the real world, that's not true, because well, for one, all tastes are different, and what I like, you may not like. What you like, I may not like. So there are corner cases. But let's assume we can always absolutely, in this case, assign a true label, and there exists a function F that does exactly that, assigns a true label. No, that's what it says. So for all I, for all possible samples, F, the function F, assigns a true label to a sample x sub I. So now that was our setting of entities that we operate with. Basically, let me go back just a second. Basically, what's on this screen is formalization of what I verbally told you on the previous screen with the Pacific Island. It's just we have assigned a precise mathematical notation to the task or story about needing to pick papayas or classify papayas as tasty or not by their hardness, so touch, how they feel, and how they look, by those two parameters. Now, we haven't done anything yet, just simply formalized it. But in order to solve the problem, simple formalization of all the parts is not enough. We need to set up a measure of success. So let's first set up or define the true loss. The loss that measures of success when we know everything and have access to all the data. What we do here, we say that for all possible subset A of our domain chi, probability of this subset is how likely we observe x within that subset. So probability of subset of our domain A is just the likelihood of observing x within A when you pick a random x. Oh, clear? Okay, I assume so. A is an event expressed as a mapping from our domain to 0, 1. That is, an event either happens or not, which we just formalize that A is a set of such samples x in our domain chi for which our indicator function is 1. That's clear, right? Nothing interesting there. But once we define everything like that, then we can say that probability of pi of x being 1, or just probability of pi of x because it's either 1 or 0, with respect to the data distribution is the same as probability of our event A. That is probability of how likely, probability of observing randomly, again, I stress that, probability of observing a randomly sampled x within an A. And it's the same as saying, right, if this is our domain chi, and this subset of this domain A, which is nothing but A, is a subset of chi, right, here. Then if we randomly sample an x, d of A, or this expression just tells us, say pi is 1 in this box and 0 outside. That's what this pi will tell us, that is this 0 and 1. I hope that's clear. Then we can define our loss, like we're defining it like that, as probability of a randomly sampled x, or probability that on a randomly sampled x, our classifier or predictor will return a label different from what the true labeling function would return. Remember, loss now is probability of an error, probability of incorrect label return. This is also called generalization error, the risk, the true error of H of our hypothesis, or simply loss. This loss of hypothesis H with respect to data distribution and true labeling function. Okay, I hope we can move on because I am moving on. So that was the true loss, an abstract notion. But empirical loss is slightly different, right? Because we don't have all possible data. So given a training set S, which is a randomly sampled subset of chi, what can we optimize? We can optimize empirical loss or error with respect to those samples. So our expected predictor or predictor that we will get in this way is H with a subscript of S. So this predictor we can optimize or have optimized on a subset of the whole data, right? It still maps any member of the domain to a label, but we found an H that minimizes loss with respect to a known D and F on that training sample. So we're minimizing loss on the training sample. And once we do that, we can define our empirical loss. And now we can do empirical risk minimization. So this loss is with respect to a training set, and it computes an error or a loss, an expected error of that learner. And if you parse this is nothing but a number of incorrect samples over the number of total samples in the training set, what we usually call accuracy. But this is an incorrect is defined here. So H of X sub I is whatever our classifier returns or hypothesis returns. So we count in this set only those I's for which the label is not equal to the true label. Remember how we defined our S is a set of, or sequence rather, of pairs. So we already have both of them, X and Y. And the last one is XM, YM, right? And okay, I should have done this somewhere in between. There's XI and YI. So we have all those pairs, and we just count our error on the training set S, and this is our empirical loss. So we may be able to estimate a classifier that does well on the training set, but what we really want is a classifier that does well with respect to the true loss. That's clear. What we usually want is a classifier that generalizes well. So wouldn't that work? This is a nice measure. Collect the training set, optimize the empirical risk, on the training set, and you're good. What can go wrong there? Well, let's consider this example. So we have our papayas. There is softness axis and there's the color axis. So if for some reason in that space, imagine that our ripe papayas or tasty papayas is everything that falls within this square. A papaya with a combination of two features, x and y, well, x1 and x2, that falls within this square is actually a tasty papaya. The label is 1. And a papaya's properties that fall outside is a bad papaya. The label, well, too brown, too green. You see what those axes are. So this is our true labeler function. That's how F would assign the labels. So we collect the training subset, which is squares and circles. So those are training subset samples. This is all that we collected, right? We couldn't buy thousands of papayas and sample them. So we bought a few, well, quite a few actually, and many of them were bad. Yuck. So I train a classifier, or my learning algorithm tells me, oh, okay, I can minimize your empirical error completely to 0, minimum possible. And what I will do is the following. If you give me a new papaya, I will check if this is the same, if it has exactly the same combination of properties as something that I've seen before, one of those blue and red samples, then I will return the label. Then I will return if that x sub I that has exactly the same properties is tasty, I will return 1. If it's not good, if it's not tasty, I will return 0 here. But if, say, a new papaya falls here, or here, or here, or anywhere, I will return 0. So look, my empirical risk is 0 here. My accuracy is perfect. Empirical loss is 0. But my true loss will be still 1/2, because the prediction will be random. My training sample is too small to overwhelm all of the possible samples. So that's not what we want, right? That's called overfitting. If we define empirical loss and we optimize empirical loss just like that without any further considerations, we will overfit, because the learner will give us a classifier that performs perfectly on the training set, minimizing empirical loss, and doesn't perform on the samples outside of the distribution at all. What can we do about that?